On the night of August 15th, 1977, a radio telescope in Ohio was doing what it had been doing for years, listening. Not to music, not to weather, not to the chatter of satellites, or the noise of passing aircraft. It was listening to the deep, cold frequency of space itself. Specifically, it was listening on a frequency that physicists believe any intelligent civilization in the universe would use to broadcast a signal, if they ever wanted to be heard. The telescope had been scanning the sky for 3 years at that point, sweeping slowly, methodically, like a lighthouse beam in reverse. Instead of sending light outward, it was drawing signals inward, collecting radio waves from the cosmos and feeding them into a computer that printed the data on long paper readouts. Most nights, the data was unremarkable. Background noise, static. The universe, for all its vastness, tends to be quiet at the frequencies we're listening on. The researchers at the Big Ear Observatory had grown used to this. You don't do this kind of work if you expect immediate results. You do it because the question is worth asking, even if the answer never comes. But on that August night, something arrived. For exactly 72 seconds, the telescope received a signal so strong, so perfectly structured, so precisely tuned to the exact frequency that scientists had theorized extraterrestrial intelligence would use, that when a researcher named Jerry Eman reviewed the printout 4 days later, he did something scientists almost never do. He picked up a red pen. He circled the data, and in the margin, he wrote one word. Wow. That notation has given the signal its name ever since. The Wow signal. 47 years have passed. We have aimed every instrument we have at the region of sky it came from. We have listened on that frequency thousands of times. We have developed theories, run simulations, argued in academic journals, and proposed explanations ranging from the mundane to the extraordinary. And we have never heard it again. We have never explained it. What you're about to hear is the full story of the most compelling and mysterious signal in the history of radio astronomy. It is a story about science, about silence, about the strange loneliness of asking a question and not knowing if anyone answered, about what it means to receive something once, something perfect, something impossible, and then have it vanish, as if it was never there at all. Get comfortable. Let the world outside fall quiet. Because this is one of the strangest and most beautiful mysteries our species has ever encountered. The ear that listened to understand the wow signal, you first have to understand the machine that caught it. The Big Ear Radio Telescope sat on the grounds of Ohio Wesleyan University, about 30 miles north of Columbus, Ohio. It wasn't glamorous. It didn't look like the soaring dish structures you might picture when you think of radio astronomy. The iconic bowl-shaped antennas aimed at the sky like mechanical flowers. Big Ear was different. It looked, if anything, a bit like a flattened football field made of aluminum. It was enormous, nearly 2 football fields long, but it lay almost flat against the Ohio landscape. A low, reflective sprawl that most passers-by probably mistook for some kind of industrial installation. It worked by reflecting radio waves off 2 flat panels, one fixed on the ground, one tilted at the far end, focusing them onto a series of receiver horns. The telescope didn't move in the way you might imagine. Instead, it relied on the Earth's rotation to sweep across the sky. Each day, as our planet turned beneath the stars, different regions of the sky drifted through Big Ear's field of view. Each section of sky was visible to the telescope for approximately 72 seconds per day as the Earth rotated it into and then out of the antenna's narrow beam. 72 seconds. That number will matter later. Big Ear had been dedicated since 1973 to a specific mission. It was part of SETI, the search for extraterrestrial intelligence. This was, even then, a project that many in the scientific establishment viewed with skepticism. Looking for alien signals felt less like science, and more like science fiction to many researchers. The odds seemed vanishingly small. The The distances were incomprehensible. The likelihood of finding anything seemed almost insulting to rational probability. But a small, committed group of scientists disagreed. They argued that if intelligent life existed elsewhere in the universe, and given the sheer number of stars and planets, it seemed statistically reasonable to suppose it might. Then radio waves were the logical medium for communication across interstellar space. Radio waves travel at the speed of light. They can penetrate the dust clouds that block visible light. They're relatively cheap to produce, energetically speaking. And there's a specific frequency band, sandwiched between the natural emission frequencies of hydrogen and hydroxyl molecules, that is unusually quiet, free of the background noise that clutters most of the radio spectrum. Astronomers called this band the water hole, because hydrogen and hydroxyl together make water, and because it was seen as a natural gathering place, a cosmic watering hole where different civilizations might meet, listening on the same quiet frequencies, waiting to hear something that didn't belong. The water hole spans a range of frequencies, but one in particular stood out: 1420.406 MHz. This is the frequency at which neutral hydrogen atoms naturally emit radio waves. Hydrogen is the most abundant element in the universe. Any civilization advanced enough to have radio telescopes would know about it. It would be, many scientists argued, the obvious choice for a beacon frequency. The universal hailing channel. The first thing you'd tune to if you wanted to be heard, or if you were trying to hear. It's worth taking a moment to appreciate just how elegant this idea is. Hydrogen is everywhere. It fills the space between stars. It was forged in the first minutes after the Big Bang and has been drifting through the cosmos ever since. When you look up at a clear night sky and see the faint smear of the Milky Way, that soft, cloudy river of light, you're looking through a galaxy that is saturated with hydrogen. Any civilization anywhere in any galaxy would encounter hydrogen. Any civilization that developed the science of spectroscopy, of measuring the light and radio emission of atoms, would discover that hydrogen rings out at 1420.406 MHz, like a bell struck at the birth of the universe. If you wanted to choose a frequency that all minds in the cosmos would know, regardless of their biology or culture or history, that would be it. The frequency of the most common thing there is. Big Ear listened on this frequency, night after night, year after year, and for 3 years it heard nothing unusual. The project was run largely by volunteers and underfunded researchers who believed deeply in what they were doing despite the skepticism of their peers. The computer that processed the telescope's data was slow by any modern standard. It could only analyze a narrow slice of the radio spectrum at a time, and its output was printed on paper in a format that had to be read by human eyes. Numbers and letters filled the pages in grid form, with each character representing the intensity of the signal received. A blank space meant no signal. The letter A meant a signal slightly above background noise. As intensity increased, the letters climbed the alphabet. Numbers represented intensities above that. The higher the number, the stronger the signal. Background noise typically produced a smattering of low letters and occasional digits, the baseline hum of the universe, converted into characters on a page. Most days the printouts were quietly boring, and the researchers who combed through them, page after page, column after column, were performing an act of enormous faith. Faith that the question was worth the patience it demanded. That somewhere in all that data, something might one day be different. The night it happened, August 15th, 1977. The telescope was running automatically as it usually did. The equipment hummed in the Ohio night. Data was being collected and fed into the computer. No one was watching in real time. The data would be reviewed later, as was standard procedure. The sky turned slowly overhead, pulling new regions of the cosmos into the telescope's patient field of view. Sometime around 11 p.m. Eastern Time, the telescope's beam swept across a particular region of the sky, a patch of space in the direction of the constellation Sagittarius, roughly 6 degrees south of a star called Sagittarii. The Earth continued to rotate. The signal, whatever it was, drifted through the beam, and then it was over. The computer recorded it. The characters were printed on the paper readout in the same font as all the noise that surrounded them. Nothing announced itself as extraordinary. There was no alarm, no flashing light, no moment of recognition. The extraordinary and the mundane sat side by side on the same page, indistinguishable without careful human attention. 4 days later, on August 19th, a volunteer researcher named Jerry Eamon sat down with the latest batch of printout pages. Eamon was a careful, methodical man, a former professor who brought the same disciplined attention to reading data that you might bring to grading exams. He went through the numbers column by column, row by row. Most of it was routine, and then he saw it. In the column corresponding to the hydrogen frequency, 1420.406 MHz, the characters read 6EQUJ5. Let that sequence sit for a moment because it looks random, but it isn't. Each character represents a signal intensity. The 6 means the signal was 6 times above background noise. Then E, which in this encoding system represents 14 times above background noise. Then Q, 26 times. Then U, 30 times. Then J, 19 times. Then 5 times. That pattern, starting low, rising sharply to a peak of 30 times background noise, then falling away again, is exactly what you would expect to see if a powerful, narrow-band radio source were moving through the fixed beam of a telescope as the Earth rotated. The signal rose as the source entered the beam, peaked as it passed through the centre, and faded as it left the other side. The shape matched perfectly. Not approximately. Perfectly. Jerry Eamon looked at the characters for a moment. He thought about what he was seeing. He checked it again. He thought about the frequency, the hydrogen frequency, the exact channel everyone agreed would be the logical choice for an interstellar broadcast. He thought about the intensity, 30 times background noise, stronger than any natural signal they'd recorded from that direction. He thought about the shape, the clean rise and fall of a source moving through the beam, consistent with something fixed in the distant sky rather than something close and moving like a satellite. He picked up a red pen. He circled the sequence, and in the margin, in neat handwriting, he wrote, "Wow." That annotation, that small, human, utterly unscientific word, became the name of the most extraordinary signal ever recorded in the history of SETI research. What made it so strange? Now let's slow down, because the wow. Signal wasn't remarkable just because it was strong. It was remarkable because of how many boxes it checked simultaneously, how precisely it seemed to match the theoretical profile of exactly what an extraterrestrial transmission would look like. First, consider the frequency. The signal came in at or extremely close to 1420.406 MHz. The hydrogen line. This wasn't a guess or an approximation. Big Ear was specifically tuned to this frequency, and the signal arrived right on it. If you were designing an alien broadcast to be noticed by any civilization advanced enough to have radio telescopes, you would choose this frequency, and whatever produced the wow signal chose it too. Second, consider the bandwidth. The signal was extremely narrowband. Natural astrophysical phenomena, pulsars, quasars, supernova remnants, tend to emit radio waves across a wide range of frequencies simultaneously. They're broadband emitters. The wow signal, by contrast, appeared to be confined to a very narrow slice of the spectrum, so narrow that it suggested an artificial engineered source. Natural processes don't tend to produce narrowband signals. Technology does. Think about the difference between a candle and a laser pointer. Both produce light, but a candle scatters photons in every direction across a broad range of wavelengths. A laser concentrates them into a tight, coherent, single wavelength beam. Natural astrophysical sources are candles. The wow signal behaved like a laser. Third, consider the shape. As mentioned before, the signal's intensity profile, rising, peaking, falling, matched exactly what you'd expect from a fixed distant source being swept through the telescope's beam by Earth's rotation. This rules out something close and moving fast, like a satellite or aircraft. It points towards something very far away and effectively stationary relative to the sky. Fourth, consider the polarization. Though the data on this point is less definitive, the signal's characteristics were consistent with a circularly polarized wave, another feature sometimes associated with artificial transmissions rather than natural ones. Fifth, and most haunting of all, the signal was never repeated. In the hours, days, weeks, and years that followed, researchers pointed every instrument they could at that region of the sky and heard nothing. The signal had come once, perfectly, and vanished. Every explanation for what it could have been has to account for all of these features simultaneously. That's what makes the wow signal so difficult to dismiss and so difficult to explain. If it were a natural astrophysical phenomenon, it would need to be one that produces narrow-band, hydrogen-frequency radio waves with the exact beam profile expected from a distant fixed source, and then never repeats. Nothing we know of does that. If it were radio frequency interference from Earth, military transmission, a satellite uplink, some piece of equipment on the ground, it would need to precisely mimic the profile of a distant cosmic source while landing exactly on the hydrogen line, and it would have to disappear permanently afterward. If it were an alien signal, it would be the most important discovery in human history, and we'd have lost it. None of these options are comfortable. The search that followed, when a man's annotation became known to the wider SETI community, it sparked an urgent response. Researchers at Big Ear and elsewhere turned their attention immediately to the sky region where the signal had originated. They listened. They kept listening. Night after night, the telescope swept across the relevant patch of Sagittarius sky, and the data came back empty. Over the following months and years, the Big Ear team, along with researchers at other observatories, directed additional effort at that same region of the sky. Other radio telescopes, larger, more sensitive, were aimed at it. The Very Large Array in New Mexico swept it. Harvard's META project listened. Australian observatories monitored the southern extensions of the same region. The target area was watched more intensively than almost any other patch of sky in radio astronomy history. Nothing. It's worth pausing to really sit with that. The wow signal arrived with a clarity and with precision that left a respected scientist momentarily speechless. And then it never came back. For 47 years and counting, that region of the sky has been silent. This creates a profound interpretive problem. Science generally depends on repeatability. When something happens once and never happens again, it becomes extremely difficult to study. You can't run experiments on a phenomenon you can't reproduce. You can't gather more data. You can't test hypotheses the way science normally works. You're left with a single data point, a single 72-second interval of information, and everything else is interpretation. In 1987 and 1989, Eamon himself re-examined the original data exhaustively, looking for any technical explanation he might have missed. He was thorough and honest in a way that reflected well on his scientific integrity. He wanted to believe there was a mundane explanation. He looked for reflections from terrestrial sources, problems with the equipment, known satellite orbits that might have caused the reading. He couldn't find one. "I think it's the most likely candidate for an alien signal that we've ever received," he said in later interviews. But he was careful to add that one detection, without confirmation, is not proof of anything. Science requires more than a single data point. The wow signal was compelling. It was not confirmation. That tension between what the data seems to suggest and what science requires to establish truth has defined the signal's legacy ever since. and it has placed the researchers who study it in an unusual position, unable to claim discovery, unable to dismiss what they found, suspended indefinitely between knowing and not knowing. There is a particular kind of intellectual purgatory in that. You have seen the most extraordinary piece of data in the history of your field, and you cannot do anything with it. You cannot publish a paper declaring contact. You cannot walk away from it either. You can only keep listening and waiting and wondering if the next sweep of the beam will bring the signal back. It never has. The candidates. Over the decades, researchers have proposed a range of explanations for the WOW signal. Some are more plausible than others. All of them have problems. Let's walk through them. The satellite hypothesis. One of the most persistent alternative explanations involves radio frequency interference from a satellite or spacecraft. Military satellites, in particular, sometimes transmit on frequencies that are theoretically restricted, including frequencies near the hydrogen line. Could the WOW signal have been a military satellite transmission that happened to land near 1,420 megahertz? The problem with this explanation is significant. The WOW signal's intensity profile, that clean rise and fall, is consistent with a source at effectively infinite distance, moving only because the Earth is rotating beneath a fixed point in the sky. Satellites are close and fast. Their signal profiles look different. Additionally, no known satellite orbit in 1977 corresponds to the position and behavior of the WOW signal source, and satellites, unlike the WOW signal, tend to produce repeatable patterns. Military satellites can't be fully ruled out because we don't have complete records of every transmission ever made. But the evidence points away from this explanation rather than toward it. The geometry doesn't fit, the profile doesn't fit, and the non-repetition is particularly hard to explain if the source were an object in Earth orbit. Satellites come around again. The interstellar comet hypothesis. In 2017, an astronomer named Antonio Paris put forward a new hypothesis that got significant media attention. He proposed that the WOW signal might have been caused by hydrogen clouds surrounding comets passing through the field of view. Comets, it turns out, do emit hydrogen. They carry water ice that breaks apart in sunlight, releasing clouds of hydrogen gas that can radiate at the 1,420 megahertz frequency. Paris identified two comets, 266P/Christensen and 335P/Gibbs, that were in the general vicinity of the sky in 1977 and suggested they could explain the signal. The response from the broader scientific community was skeptical, and not without reason. First, comets are far too close to Earth to produce the intensity profile the WOW signal displayed. A comet's signal would not look like a fixed point at cosmic distance sweeping through the telescope beam. It would look very different and much weaker. Second, and more importantly, the hydrogen emissions from comets are broadband. They spread across a wide range of frequencies. The WOW signal was narrowband. This is a fundamental mismatch that the comet hypothesis doesn't adequately resolve. Third, comets are in motion. Their signals drift in frequency as they move, a Doppler shift caused by their velocity relative to Earth. The WOW signal showed no such drift. It sat precisely on the hydrogen frequency without deviation. Most SETI researchers rejected the Paris hypothesis as insufficient. Jerry Amon himself reviewed it and found the explanations unconvincing. The comet hypothesis was worth considering, as all hypotheses are, but the data doesn't support it. Each objection is fundamental, not merely technical. The comet hypothesis doesn't explain the narrowband character. It doesn't explain the lack of frequency drift. It doesn't explain the intensity profile. It explains very little, actually, while creating new problems. The natural astrophysical source. Hypothesis. Could there be some natural phenomenon, something we haven't discovered or don't fully understand, that produces narrowband radio bursts at the hydrogen frequency? Something that fired once in our direction and hasn't since? It's conceivable. The universe is full of phenomena that surprised us. Pulsars, rapidly spinning neutron stars that emit radio beams like cosmic lighthouses, were themselves once mistaken for alien signals when first discovered in 1967. The researchers who found them at Cambridge University were so unsettled by the regular structured pulses that they initially labelled the source LGM1, Little Green Men 1, as a half-joking acknowledgement of what the data looked like. Fast radio bursts are another example, mysterious, millisecond-long pulses of radio energy that arrive from cosmological distances, discovered only in 2007. We still don't fully understand them. They demonstrated that the universe is capable of producing powerful, brief, structured radio events that confounded initial understanding. But natural sources face the same fundamental challenge when applied to the wow signal, the narrowband nature of the signal. Astrophysical processes tend to produce broadband emission. The narrower the bandwidth, the more it points towards something engineered, designed to concentrate energy into a small slice of the spectrum rather than spreading it across many frequencies. No natural phenomenon we've identified does this reliably at the hydrogen frequency. That doesn't mean none exists, it means we don't have one to point to. The terrestrial interference hypothesis. Some researchers have suggested that the signal came from the Earth itself, a ground-based transmitter of some kind, reflecting off the antenna in an unusual way, or a piece of military or government equipment operating on a restricted frequency. The difficulty here is that Big Ear was designed to help filter out terrestrial interference. It used two separate beams pointing at slightly different parts of the sky simultaneously. A terrestrial signal would typically appear in both beams. The wow signal appeared in only one beam, the one pointed at the sky, and not in the other. This is the expected behaviour for a signal coming from space. Additionally, transmitting on the hydrogen frequency was illegal under international radio regulations, even in 1977. That doesn't mean it never happened, but it raises the bar for this explanation, the extraterrestrial intelligence hypothesis. And then there is the explanation that fits the data best, even if it's the hardest to accept. The wow signal looked like what a deliberate broadcast from another civilization would look like. It arrived on the right frequency. It had the right bandwidth. It had the right shape. It was strong enough to be detectable from interstellar distances. It was never heard again, which could mean it was a targeted or sweeping transmission that only reached us once, like a lighthouse beam that takes years to complete each rotation. There's a version of this possibility that's especially evocative. Imagine a civilization broadcasting a repeating signal, a beacon designed to be noticed, that sweeps through the sky the way a lighthouse sweeps through the dark. If the rotation period of that sweep is long enough, a given point in the sky might only pass through the beam once every few decades or centuries. We happened to be listening on the right frequency at the right moment, and we caught one pass. And then the beam moved on. The problem, as always, is that we can't confirm it. We have one data point. Science needs more. Without a second detection, without a repeating signal, without any corroborating information, we cannot say with any scientific rigour that the wow signal was a message from another civilization. We can only say that it matches the profile of what such a message would look like better than any other detected signal in history. That's a significant thing to say. It's not the same as proof, but it isn't nothing either. The place it came from. Let's talk about where the signal came from, or at least where in the sky it appeared to originate. The source was located somewhere in the direction of the constellation Sagittarius. More precisely, it came from a region near the star Chi Sagittarii. Though the precision of 1977-era radio telescopes wasn't fine enough to pinpoint an exact location. What we know is a general region of the sky, a patch of space in the direction of the galactic centre. This is interesting for reasons beyond the merely astronomical. Sagittarius lies in the direction of the core of our own Milky Way galaxy. The galactic centre is dense with stars, ancient stars, many of them billions of years old, orbited by planets that could have been habitable for far longer than our own solar system has existed. The Sun is a relatively young star. Its planets formed about 4.5 billion years ago. But stars in the inner galaxy are often much older. Some date back 10 billion years or more. If intelligence emerges wherever conditions allow it, and if it takes roughly the same amount of time to emerge on every world, then the inner galaxy might be populated with civilizations that are billions of years older than ours. Billions of years older. Think about what that means. Our civilization, as measured by our ability to build radio telescopes, is perhaps a century old. A civilization that had a billion-year head start on us might be as far beyond us as we are beyond the bacteria that first produced oxygen in Earth's primordial oceans. We couldn't begin to imagine what they've built, what they know, how they communicate, or what they'd want to say to us, if they know we exist at all. But the signal's actual distance is unknown. It could have come from a star 30 light-years away or 3,000. Radio waves carry no natural timestamp telling us how far they've travelled. We know the direction. We don't know the depth. Some researchers have tried to identify candidate stars within the broad search area that might host habitable planets. The list includes several Sun-like stars within a few hundred light-years. None have been definitively linked to the signal. None have shown unusual radio emissions, but none have been exhaustively investigated either. The silence of that region of the sky since 1977 is its own kind of data. Whatever sent the signal, if anything intelligent sent it, has not sent another that we've detected. Or if it has, we haven't been listening at the right moment. Or the beam has moved on, and we're waiting for the lighthouse to come around again. There is something almost vertiginous about contemplating this. A signal arrives from somewhere in that direction of the sky. It lasts for 72 seconds, and then an incomprehensible distance of space closes back over whatever was there, and we're left looking at a spot in the night sky with no way to reach it, no way to ask again, no way to know if anything was listening. For our answer, the response we sent. In 2012, 35 years after the signal was received, a group organised by National Geographic sent a response in the direction of the WOW, signal's apparent origin. It was a crowdsourced message. Thousands of Twitter responses from people around the world, compressed into a transmission and broadcast from the Arecibo Observatory in Puerto Rico. It was a beautiful gesture, symbolic, heartfelt, and almost certainly limited in any practical sense, because we don't know the exact source, and because even if we did, a radio transmission travels at the speed of light, meaning any response we send today wouldn't arrive at even a nearby star for decades. If the signal came from somewhere 30 light-years away, our reply won't get there until 2042, and we'd have to wait another 30 years after that for any acknowledgement to reach us. This is the fundamental challenge of interstellar communication. Even at the speed of light, the fastest anything can, travel in this universe, conversation across the stars unfolds on timescales that dwarf human lifetimes. The entities that sent the WOW signal, if they exist, don't know we heard them. They don't know we're still listening. They might have changed beyond recognition in the intervening decades. Their civilization might have transformed itself in ways we cannot conceive. Or it might no longer exist. And we sent a reply they might not recognize to a location we can't precisely specify, from a planet that may not be distinguishable from background noise at interstellar distances. This is not pessimism. It's the universe, honestly stated. The distances are real. The silence is real. And the attempt to reach across it anyway, that's also real. There is something quietly noble about a species that shouts into the dark, even knowing the dark may swallow the sound whole. We replied, even knowing the odds, that impulse, to answer, to reach out, to say we heard you even without. Certainty that we did is one of the more beautiful things about being human. The science of listening. Since 1977, SETI research has evolved enormously. The tools are more sophisticated. The computers are incomprehensibly faster. The range of frequencies we can monitor simultaneously has expanded from a narrow slice to a broadband coverage that would have seemed like magic to the researchers at Big Ear. The Allen Telescope Array in Northern California, partially funded by Microsoft co-founder Paul Allen, was designed specifically for SETI research and can monitor millions of frequency channels simultaneously. The Breakthrough Listen initiative, funded by entrepreneur Yuri Milner and backed by scientists including the late Stephen Hawking, began in 2015 with a $100 million commitment to the most comprehensive SETI survey ever attempted. It uses some of the world's largest radio telescopes to survey millions of stars and hundreds of galaxies across a wide range of frequencies, and yet, despite better tools, wider coverage, more computing power, and decades of additional listening, we have not found another signal like the wow signal. We haven't found anything that comes close. This is either discouraging or meaningless, depending on how you look at it. The universe is enormous beyond easy comprehension. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. Each star may host one or more planets. We have surveyed a vanishingly small fraction of the sky, at a limited range of frequencies, for a relatively short period of time, with instruments that have fundamental limitations. The absence of a second signal tells us something, but not as much as we might hope. Think of it this way. Imagine you're standing in the middle of an ocean and you want to know if there are fish in it. You lower a single small net, haul it up, and find it empty. Does that mean there are no fish? Of course not. The ocean is vast. Your net is small. A single empty haul is not a meaningful data point when the search space is that large. SETI research faces the same problem, scaled up to cosmic proportions. This silence so far doesn't mean no one is out there. It means we haven't found them yet, or that we're not looking in the right place, or on the right frequency, or at the right time, or that they're broadcasting in a way we don't yet know how to recognize. The wow signal doesn't resolve this problem, but it does complicate the silence, because if we heard nothing for 50 years, we might comfortably settle into the assumption that we're alone. But we didn't hear nothing. We heard something once, something extraordinary, and then we heard nothing again. That's a different kind of silence, charged rather than empty. The Fermi paradox and the quiet sky, the wow. Signal exists in a broader context, a puzzle that has troubled physicists and astronomers since the 1950s. The puzzle is this. Given the age of the universe, roughly 13.8 billion years, given the vast number of stars and planets it contains, given that life on Earth emerged relatively quickly after the planet formed, it seems statistically reasonable to suppose that intelligent life should have evolved elsewhere, perhaps many times over, perhaps billions of years before us. If that's true, where is everyone? In 1950, the physicist Enrico Fermi articulated this question during a casual lunch conversation with colleagues. The universe is old. The distances between stars are vast but not uncrossable given sufficient time and technology. A civilization that developed interstellar travel even 1 million years ago, a blink of an eye in cosmic time, could theoretically have colonized the entire galaxy by now. Yet we see no evidence of this. We see no megastructures. We receive no signals. We detect no signs of engineering on a cosmic scale. This became known as the Fermi paradox, and in the decades since it was articulated, it has become one of the most profound and unsettling open questions in science. There are many proposed resolutions. Perhaps intelligent life is rarer than we think, and we are genuinely alone or nearly so. This is sometimes called the rare Earth hypothesis. The idea that the particular combination of factors that produced complex life on Earth, the right kind of star, a stable orbit, a large moon stabilizing our axial tilt, plate tectonics, a magnetic field, a giant planet like Jupiter deflecting incoming asteroids, is so improbable that it may have occurred only once in our galaxy, or only a handful of times. Others propose what's grimly called the Great Filter, some barrier that nearly all civilizations fail to cross. It could be behind us, Perhaps the emergence of complex, multicellular life is extraordinarily rare, and we've already survived the worst of the cosmic odds. Or it could be ahead of us. Perhaps every civilization that reaches our level of technological development eventually destroys itself through war, environmental collapse, engineered pathogens, or the misuse of whatever their equivalent of nuclear weapons turns out to be. If the filter lies ahead, that is a deeply sobering thought. Others suggest that the galaxy is in fact populated, but that civilizations are deliberately quiet, listening rather than broadcasting, for reasons we can only speculate at. Perhaps broadcasting is considered dangerous. Perhaps sophisticated civilizations recognize that announcing your presence to an unknown galaxy is not obviously wise. Perhaps they're out there, watching, waiting to see what we do with our technology before deciding whether to say hello. Or perhaps, and this is the possibility that the wow signal keeps alive in its quiet, stubborn way. They're broadcasting, and we've caught a glimpse, just once, just barely, just enough to know that something is out there without knowing where or who or what. The Fermi paradox makes the wow signal both more significant and more frustrating. If we're alone, the signal needs an explanation, a natural one. If we're not alone, the signal might be the one moment our species and another briefly shared the same frequency, without either one knowing if the message was received. Both possibilities are extraordinary, neither is comfortable. Jerry Eman and the weight of a discovery. It seems worth spending a moment with the man who found it. Jerry Eman didn't set out to make history. He was a volunteer, a former professor who gave his time to the Big Ear Project because he believed in what they were doing, even when the funding was thin and the results were nothing. He drove to the observatory, reviewed data printouts, and drove home. He did this for years without fanfare, without recognition, as part of a community of dedicated people who believed that the question of cosmic companionship was worth taking seriously, even when the rest of the world wasn't paying attention. And then one afternoon in August, sitting with a stack of papers at a desk in Ohio, he saw 6 characters that would follow him for the rest of his life. He described the moment in later interviews with a kind of careful, almost reluctant awe. He didn't want to overstate it. He wasn't someone who leapt to conclusions or courted drama. He was a scientist, trained to distrust first impressions, to check and recheck, to look for the simpler explanation before reaching for the extraordinary. So he checked and checked again, and couldn't find a simpler explanation. The word he wrote in the margin, wow, is deceptively simple. It's not a scientific term. It doesn't appear in any journal article or technical report in quite the same way. It's just the honest response of a human being confronting something that exceeds easy explanation. In that sense, it might be the most authentic scientific annotation ever made. Not significant anomaly noted for further investigation. Not possible candidate signal requiring confirmation. Just wow. Just the raw, unfiltered response of a person who has seen something they don't have words for yet. Eman spent the rest of his career analysing and reanalyzing the signal, looking for the flaw in his reasoning, the mundane explanation he might have missed. He never found one that satisfied him. He remained professionally cautious, unwilling to claim the signal was definitely extraterrestrial without the confirmation that never came. But he also never found a compelling reason to dismiss it. There's something quietly poignant about that position. To be the person who found the best candidate for alien contact in human history, and to spend decades unable to confirm it, unable to rule it out, holding a question that the universe refuses to answer, to carry that annotation, that red-penned circle on a paper printout, through a lifetime of continued listening and sustained uncertainty. He passed away in 2023 at the age of 84 with the question still open. The signal he found has outlasted him. It remains, as it always was, circled, annotated, unexplained. What 72 seconds means. Let's think carefully about the number 72. The wow. Signal lasted for exactly as long as it was expected to last, Given the telescope's design and the Earth's rotation rate, a source fixed in the distant sky would pass through Big Ear's beam in approximately 72 seconds. No more, no less. The signal obliged perfectly, which is itself part of what makes it so remarkable. It didn't come in too long or cut off too early. It traced the exact arc that physics predicted, as if whatever made it knew exactly what kind of instrument would be receiving it. But here's what's interesting to contemplate. Those 72 seconds represent the entirety of our data. All of it. Everything we know about this signal, every feature, every measurement, every characteristic we've analysed, fits inside just over a minute. There's no second observation to compare it to. No follow-up measurement that might clarify the bandwidth or reveal structure we initially missed. No way to study its properties in more detail because we only ever had one pass. In 72 seconds, a child can learn to tie a shoe. You can boil an egg. You can read a short poem aloud. You can walk to the end of the block and back. You can have the brief, inconclusive phone call that changes everything or nothing. In 72 seconds, something from somewhere in the cosmos, or perhaps something from our own technological civilization, though the evidence points away from this, passed through a radio telescope in Ohio and left us with one of the most profound unanswered questions our species has ever held. That's the scale at which the universe communicates with us, at least so far. 72 seconds of data, then silence, then decades of wondering. There's something almost haiku-like about this. The universe compressing whatever it had to say, or whatever it accidentally revealed, into a brief, crystalline moment that arrived and departed before anyone even knew it was there. Before Jerry Eamon sat down with his stack of papers. Before anyone could aim another instrument at the sky and say, "Wait, what was that?" Say it again. If it was a message, we don't know what it said. If it was a natural phenomenon, we don't know what caused it. If it was a mistake, our own technology misfiring in some unrecorded way, we don't know how to demonstrate that either. 72 seconds. That's all we have. And it may be the most important 72 seconds our civilization ever recorded. The philosophical weight set aside the science for a moment. Set aside the hypotheses and the data and the frequency calculations. Let's sit with what the wow signal means at a deeper level. Human beings have been looking at the stars for as long as we've been human. Our ancestors named constellations, built temples aligned to the solstices, navigated oceans by starlight, composed myths and cosmologies to make sense of the lights above. The night sky has always been, for our species, a place of mystery and meaning, a ceiling of wonder above the brief bright window of each individual life. And somewhere in that long history of looking upward, we started to wonder whether the lights were looking back. Are we alone? It's perhaps the most fundamental question we've ever asked about ourselves. It shapes how we understand our own significance. If we are alone, if this planet, this biosphere, this improbable cascade of chemistry and time that produced consciousness and language and radio telescopes, if all of that is unique in the universe, then we are something extraordinary beyond comprehension. The only knowers in a vast darkness, the only beings in perhaps hundreds of billions of galaxies who have looked up and asked, is there anyone else? That's either magnificent or terrifying, depending on the day. And if we are not alone, if intelligence is something the universe produces regularly, under the right conditions, given enough time, then we are members of a community we've never met, citizens of a cosmos populated with minds we cannot yet imagine, each looking up from their own world, each carrying their own version of the same question. The wow signal doesn't resolve this, but it keeps it alive in a very specific way. It provides a moment, a brief, tantalizing moment, where the data seemed to whisper, "Not alone." And then the data went quiet, and we've been trying to decide what to make of that ever since. There is a particular kind of longing that the signal evokes. It's the feeling of having almost heard something, of standing in a quiet room late at night and being almost certain you heard your name called from somewhere far away. and then stepping outside to listen and finding only the wind, or the neighbour's dog, or nothing at all. Was it real? Was it the house settling? Was it your own hopeful imagination filling the silence with what it most wanted to hear? The wow. Signal sits in that space between detection and confirmation, between wonder and certainty, between the vast hope that we are not alone and the quiet acknowledgement that we cannot be sure. And there's something strangely comforting about that, in a way that's difficult to articulate but easy to feel. The question itself is one of the most beautiful things about being human. The fact that we're sophisticated enough to build instruments that can detect signals from space, humble enough to wonder if they're messages, and persistent enough to keep listening even after decades of silence. That says something worth saying about the kind of creatures we are. We are the universe's way of asking whether it is alone, and we haven't given up on the question. The tools we're building. As we move further into the 21st century, the search for signals like the wow signal is becoming more systematic and more powerful than anything Jerry Eamon's generation could have imagined. The Square Kilometre Array, a massive international radio telescope project being constructed across South Africa and Australia, will be, when complete, the largest radio telescope ever built. Its combined collecting area will exceed 1 square kilometre. Its sensitivity will dwarf any previous instrument by orders of magnitude. It will be able to detect radio signals from distances and at signal strengths that would have been science fiction to the researchers at Big Ear. If something like the wow signal occurs again, the Square Kilometre Array will not only detect it, it will measure it with a precision and richness of data that 1977 technology couldn't have approached. Artificial intelligence is also transforming the search in fundamental ways. The raw data produced by modern radio telescopes is too vast for human reviewers to read. Unlike the paper printouts of the 1970s, today's instruments generate terabytes of data per hour. Machine learning algorithms can scan this data for anomalous signals far faster and more comprehensively than any team of human researchers. They can be trained on known interference patterns and learn to filter them out automatically. They can flag unusual signals for human review. They can learn to recognize subtle features that a human mind, skimming through mountains of data, might miss entirely. There's something almost touching about the image of an artificial intelligence scanning the cosmos for signals that another intelligence might have sent. Intelligence looking for intelligence across the void, with intelligence as its instrument. SETI has also expanded into optical searches, the hunt for laser pulses and other tightly focused beams of light that an advanced civilization might use to communicate. Radio waves are not the only option. A civilization that has mastered laser technology might choose coherent light over radio for the same reasons we chose it for fibre optic communications: efficiency, precision, bandwidth. We're now building instruments capable of detecting nanosecond pulses of laser light from nearby stars, brief flashes that would be invisible in the noise of a star's natural output, but detectable with the right technology. The search has also expanded in scope. Rather than focusing on nearby sun-like stars, some researchers now advocate for looking at globular clusters, ancient, dense gatherings of hundreds of thousands of stars, some of them billions of years older than the Sun. If intelligence requires time to develop, globular clusters might be among the oldest incubators of mind in the galaxy. Others focus more attention on the galactic centre, where stellar density is higher and ancient stars are most numerous. Others follow up, specifically on exoplanets that have already been identified as potentially habitable, worlds where the conditions for life seem at least plausible. We're not doing what the Big Ear researchers did, pointing a single telescope at a narrow strip of sky and waiting. We're doing thousands of things at once with better tools, broader vision and more computing power than the 1977 team could have dreamed possible, and the pace of improvement is accelerating. And yet the wow signal remains unique. In nearly 50 years of increasingly sophisticated searching, nothing has matched it. Nothing has come close. It stands alone in the data, circled in red, still waiting, living with the mystery. There's a strange comfort in unsolved mysteries, if you approach them in the right spirit. We live in an age of information saturation. Everything is explained, categorized, cross-referenced, and debated to exhaustion on a dozen platforms simultaneously. The experience of genuine mystery, of something that simply cannot be resolved, that sits at the edge of our collective knowledge and refuses to yield, has become rare. There are very few things left that we can look at and say, honestly, we don't know, and fewer still that we may never know. The wow signal is one of them. It sits in the archives of radio astronomy like a sealed room in a very old house. You know it's there. You can measure its dimensions from the outside. You can describe the door in detail, but you can't open it, and you don't know what's on the other side. Some people find this maddening. Scientists in particular tend to find unresolved questions uncomfortable. We are built, as a discipline, to want answers, to apply the tools of inquiry until something yields. The persistence of the wow signals mystery, after so many serious attempts to explain it, is genuinely unsettling to researchers who believe every phenomenon has a natural cause that patient investigation can eventually identify. But there's another way to hold it. You can think of the wow signal not as a failure of explanation, but as a gift of possibility. As long as it remains unexplained, every option is still on the table. The universe has not yet told us no, and that means that somewhere in the direction of Sagittarius, in that ancient star field, in that sweep of cosmic distance we can barely begin to conceptualize, there might be a civilization that is itself looking at the sky, running its own version of this same search, its own instruments pointed outward into the silence, asking the same question from the other side. They might not know they're being heard. They might not know they sent something that found us, even briefly, even incompletely. They might be asking, as we ask, is anyone out there? Are we alone? And if they are, if there is some civilization around some star in some part of that ancient sky that once sent a signal and is still wondering whether it was received, then in a very small but genuine way, the answer is yes. A researcher in Ohio circled it with a red pen. We heard you. Even if we couldn't answer, even if we're still not sure what you said, we're still listening. The long vigil. It's late now, wherever you are. The sky above you is the same sky that covered the Ohio plains where Big Ear stood, the same darkness that wraps every radio telescope from New Mexico to South Africa, from the high desert of Chile to the remote plains of Western Australia. The same endless cold that separates us from whatever is out there, whether it's natural and magnificent and without a mind to know it, or whether it is something more. The stars you can see tonight, or that are above the clouds even if you can't, have been broadcasting for billions of years. Light, radiation, neutrinos, radio waves. The universe is not silent. It is full of signal. It is saturated with information, with the ongoing record of its own history, with the accumulated output of hundreds of billions of stars doing what stars do, burning hydrogen into helium, slowly, over millions of years, in the dark. Most of that signal is natural. Most of it is the hum of stellar fusion, the cry of collapsing stars, the whisper of gas clouds drifting between galaxies. Most of it, as far as we can tell, is beautiful and mindless and magnificent. The universe doing what physics says it must, without intention or awareness, or anything we'd recognize as thought. But 72 seconds of it, on one August night in 1977, was different. Whether it was different because of something intelligent, or different because of some natural phenomenon we haven't catalogued, or different because of some terrestrial technology we can no longer trace. We don't know. We may never know. The universe made no promise to give us answers. It only made the promise it always makes, to keep being vast and old and full of things we don't understand yet, to keep going, quietly and indifferently while we try to understand it. The researchers at observatories around the world are still listening tonight. Their instruments are tuned. Their algorithms are scanning millions of frequency channels. Simultaneously, somewhere a radio telescope is pointed towards Sagittarius, and the data is being recorded and nothing unusual is coming through, and they will try again tomorrow, and the day after, as they have every day for 50 years. This is what science looks like when it's doing something genuinely difficult. Not dramatic discoveries every week, not revelations on demand, just the long vigil, the quiet, patient, decade-spanning willingness to keep asking the question, even when the answer doesn't come. To show up in the morning or the middle of the night and listen to the sky. There's a lesson in that for all of us, I think. Some questions are worth holding. Some mysteries are worth sitting with, not because you expect to solve them tonight, but because the act of wondering, the sustained, open-hearted orientation toward the unknown, is itself a kind of answer. To wonder is to participate in something larger than yourself. To listen is to acknowledge that the universe might be saying something. To keep listening, even in the silence, is to believe that it's worth hearing. The wow! Signal lasted 72 seconds. The search it helped inspire has lasted half a century. And the question behind it, the oldest, biggest, most persistently human question there is, has been with us since the first one of us looked up at the night sky and thought, I wonder if anyone else is up there, looking back. We still don't know. We're still looking. Close your eyes if you'd like. Think of that signal. Those 6 characters on a page, circled in red, annotated with one quiet word of wonder. Think of the telescope turning in the Ohio night, the Earth rotating slowly beneath the stars, the 72 seconds when something crossed the beam and left its mark on a paper printout, and then was gone. Think of Jerry Eman sitting at his desk 4 days later, moving through another ordinary stack of papers, and then stopping, picking up his red pen, writing that word, not knowing, in that moment, that he would spend the rest of his life answering questions about it. Not knowing that the annotation would outlast him, not knowing that decades later, people lying in the dark on the other side of the planet would be listening to the story of those 6 characters as they drifted towards sleep. He just saw something he couldn't explain, and he wrote what he felt. Wow! Think of the silence that followed, stretching from 1977 to now, and all the patient listening that filled it. All the people who gave their nights and their years to the question, who sat with headphones and data printouts and glowing monitors, scanning the sky for the thing that had arrived once and hadn't come back. All the telescopes that swept through that patch of Sagittarius sky, and found only the ordinary hum of the cosmos. That patience is its own kind of answer. That persistence is its own kind of statement about who we are, and somewhere out there, in the direction of the galactic centre, past Chi Sagittari, past the edge of anything we can name or reach or even fully imagine, maybe something is still broadcasting. Maybe the signal has been repeating every year since 1977, and we just haven't been pointing the right antenna at the right moment when it sweeps through. Maybe it's a lighthouse that takes 1,000 years to complete a single rotation, and we happen to be in the beam for 72 seconds, and we have 900 years left to wait before the light comes around again. Maybe the civilization that sent it has long since gone quiet, for reasons we'll never know. Maybe it was never a civilization at all. Maybe it was something the universe does that we haven't catalogued yet. Something wonderful and natural and entirely without intention. Maybe the answer is so strange we wouldn't recognize it even if it arrived. Maybe. The universe is very old, we are very young, and we are paying attention. That, in the end, might be the most remarkable thing about all of this. Not the signal itself, not the mystery, but the fact that we noticed. That out of everything we might have done with our brief, improbable existence on this small, warm planet, out of everything that competes for our attention in every waking hour, we built machines to listen to the sky. We dedicated years and careers and lifetimes to the possibility that something out there might have something to say. We circled 6 characters with a red pen and took them seriously for half a century. That's enough. For now, that's enough. Sleep well. The sky will still be there when you wake up. And somewhere in it, the question waits, patient and vast and undimmed, the same as it has always been, the same as it will always be.